Earth's heavy metals result of supernova explosion, research reveals that gold on your ring finger is stellar, and not just in a complementary way. In a finding that may overthrow our understanding of where Earth's heavy elements such as gold and platinum come from, new research by a University of Guelph physicist suggests that most of them were spewed from a largely overlooked kind of star explosion far away in space and time from our planet. Some 80% of the heavy elements in the universe likely formed in collapsars, a rare but heavy element-rich form of supernova explosion from the gravitational collapse of old, massive stars typically 30 times as weighty as our Sun, said physics professor Daniel Siegel. That finding overturns the widely held belief that these elements mostly come from collisions between neutron stars or between a neutron star and a black hole, said Siegel. His paper co-authored with Columbia University colleagues appears today in the journal Nature. Using supercomputers, the trio simulated the dynamics of collapsars, or old stars whose gravity causes them to implode and form black holes. Under their model, massive, rapidly spinning collapsars eject heavy elements whose amounts and distribution are astonishingly similar to what we observe in our solar system, said Siegel. He joined U of G this month and is also appointed to the Perimeter Institute for Theoretical Physics, in Waterloo, ONT. Most of the elements found in nature were created in nuclear reactions in stars and ultimately expelled in huge stellar explosions. Heavy elements found on Earth and elsewhere in the universe from long-ago explosions range from gold and platinum, to uranium and plutonium used in nuclear reactors, to more exotic chemical elements such as neodymium found in consumer items such as electronics. Until now, scientists thought that these elements were cooked up mostly in stellar smash-ups involving neutron stars or black holes, as in a collision of two neutron stars observed by Earth-bound detectors that made headlines in 2017. Ironically, said Siegel, his team began working to understand the physics of that merger before their simulations pointed toward collapsars as a heavy element birth chamber. Our research on neutron star mergers has led us to believe that the birth of black holes in a very different type of stellar explosion might produce even more gold than neutron star mergers. What collapsars lack in frequency, they make up for in generation of heavy elements, said Siegel. Collapsars also produce intense flashes of gamma rays. 80% of these heavy elements we see should come from collapsars. Collapsars are fairly rare in occurrences of supernovae, even more rare than neutron star mergers, but the amount of material that they eject into space is much higher than that from neutron star mergers. The team now hopes to see its theoretical model validated by observations. Siegel said infrared instruments such as those on the James Webb Space Telescope, set for launch in 2021, should be able to detect telltale radiation pointing to heavy elements from a collapsar in a far-distant galaxy. That would be a clear signature, he said, adding that astronomers might also detect evidence of collapsars by looking at amounts and distribution of heavy element S in other stars across our Milky Way galaxy. Siegel said this research may yield clues about how our galaxy began. Trying to nail down where heavy elements come from may help us understand how the galaxy was chemically assembled and how the galaxy formed. This may actually help solve some big questions in cosmology, as heavy elements are a nice tracer. This year marks the 150th anniversary of Dmitry Mendeleev's creation of the periodic table of the chemical elements. Since then, scientists have added many more elements to the periodic table, a staple of science textbooks and classrooms worldwide. Referring to the Russian chemist, Siegel said, "We know many more elements that he didn't." What's fascinating and surprising is that, after 150 years of studying the fundamental building blocks of nature, we still don't quite understand how the universe creates a big fraction of the elements in the periodic table. Plate tectonics may have driven Cambrian explosion. The quest to discover what drove one of the most important evolutionary events in the history of life on Earth has taken a new, fascinating twist. A team of scientists have given a fresh insight into what may have driven the Cambrian explosion, a period of rapid expansion of different forms of animal life that occurred over 500 million years ago. While a number of theories have been put forward to explain this landmark period, the most credible is that it was fueled by a significant rise in oxygen levels which allowed a wide variety of animals to thrive. The new study suggests that such a rise in oxygen levels was the result of extraordinary changes in global plate tectonics. During the formation of the supercontinent Gondwana, there was a major increase in continental arc volcanism. Chains of volcanoes often thousands of miles long formed where continental and oceanic tectonic plates collided. This in turn led to increased degassing of CO2 from ancient, subducted sedimentary rocks. This, the team calculated, led to an increase in atmospheric CO2 and warming of the planet, which in turn amplified the weathering of continental rocks, which supplied the nutrient phosphorus to the ocean to drive photosynthesis and oxygen production. The study was led by Josh Williams, who began the research as an MSc student at the University of Exeter and is now studying for a PhD at the University of Edinburgh. During his MSc project he used a sophisticated biogeochemical model to make the first quantification of changes in atmospheric oxygen levels just prior to this explosion of life. Co-author and project supervisor Professor Tim Lenton, from the University of Exeter's Global Systems Institute said, "One of the great dilemmas originally recognized by Darwin is why complex life, in the form of fossil animals, appeared so abruptly in what is now known as the Cambrian explosion. Many studies have suggested this was linked to a rise in oxygen levels, but without a clear cause for such a rise, or any attempt to quantify it. Not only did the model predict a marked rise in oxygen levels due to changes in plate tectonic activity, but that rise in oxygen, to about a quarter of the level in today's atmosphere, crossed the critical levels estimated to be needed by the animals seen in the Cambrian explosion." Williams added, "What is particularly compelling about this research is that not only does the model predict a rise in oxygen to levels estimated to be necessary to support the large, mobile, predatory animal life of the Cambrian, but the model predictions also show strong agreement with existing geochemical evidence. It is remarkable to think that our oldest animal ancestors, and therefore all of us, may owe our existence, in part, to an unusual episode of plate tectonics over 500 million years ago," said Professor Lenton.